So about the test that's a week from today, I don't know how many problems it's going to be. I haven't created the test. What I will do is I will create a review, okay? And this review I will send to you via email sometime in the next 2 days. And the idea is for you to look over that review over the weekend, come in here on Monday with questions over the review. We talk about the review, go over anything, and then on Wednesday we come and take the test. Okay? That's the plan. So a part of your homework for this weekend will be to do the review. And you don't have to do it all. You just have to attempt it. That way you can come in and ask questions. All right? Questions on that? All right, go ahead. We have a couple of questions over homework. What do you got? Number 17. So this is out of the homework from last time. It is the, let's see, we have a root here. It's a negative out front. It's a cube root. And then it's a negative inside 125 over 27. That's a good problem right there. I wanted to share something. A student of mine, I don't know who it was. It might be someone here. I have the memory of a fly sometimes. They do their square roots like this, and I thought it was really cool. I guess they were taught to put this little, do y'all see that little line that comes out right here? See that? I don't normally do that, but a student had shown me that's the way they do it. And what it does is it allows you a good place to put that cube root so that you don't mix it up with something else. It just allows you to have a little more space in there. It just, FYI, if you want to try that, it might help you keep things organized. All right. So what I'm going to do here in this problem is I'm going to look at the root first. It's a cube root, and inside the cube root I have a negative number. Can we take an odd root? 3 is odd, right? Can you take an odd root of a negative number? Yes. You can't take an even root of a negative number. So I know that I can get an answer here, and from last class, this answer is going to be negative. Mm-hmm. Your answer will be negative. Yep. So let me proceed with how I'm going to do this. I'm going to say that this is equal to, that negative still sitting out front. What I'm going to do here is I'm going to take the property that allows me to take a fraction inside of a root and split it into 2 roots, okay? And put the fraction, the numerator on top and denominator on bottom. The question is, what do I do with that negative that's out front? I'm talking about the one that I've highlighted in yellow, the negative inside the root. Where does it go? If I have negative 125 over 27, I can write that as negative 125 over 27, or I could write it as 125 over negative 27. In other words, when you have a negative in front of a fraction, the negative can go on top or on the bottom, but it cannot go on both the top and the bottom at the same time. So I get to make a choice here of where I want to put that negative. I'm going to choose to put the negative on the 125 and to leave the 27 as positive. Everyone see that? Does anyone have a question on that? Just because. Yep. If you wanted to, you could have put the negative on the 27 and left the 125 as a positive. Now, let's ask ourselves, what is the cube root of negative 125? So start thinking about perfect cubes. What are the perfect cubes? What's 2 cubed? What's 3 cubed? What's 4 cubed? What's 5 cubed? What's 6 cubed? Right? What cubed gives you 125? 5, right? Now, I can't have 5 as an answer. I have to have what? Because it's a negative under the cube root, your answer must be -5 on top. And then in the denominator, what's the cube root of 27? What times itself 3 times gives you 27? 3. Now, that negative that I've had sitting out here in the front the whole time, isn't that really like a -1? And the other part of my answer is -5/3. So what's a negative times a negative? Positive. So it's +5/3. So yeah, that's if you look at that negative out front as a -1 and then multiplication. Any others? Well, in this case, in this particular problem, it worked because we could get an odd root. Had the problem started out negative and then it was like 4th root, then you would have had no solution. So you would never put that negative inside and put it together with the other negative that's outside and inside if that had been a 4th root. I don't know if that answers your question, but any others off the homework? 25? So yesterday I taught I had my Calculus 2 class. I have that on Tuesdays, Thursdays. And last week we covered a pretty heavy concept on last Thursday. I said, go home, do your homework. We have a test in 1 week. And I went into class yesterday and I did a walk around my Cal 2 class. Show me your homework that you were supposed to do this weekend for a quiz grade. 3 people. That's it. Out of 26 students. 3. Cal 2 students, which I would expect so much more from, right? I mean, they should understand how important homework is. So, I guess my point, hopefully, is that you have been doing your homework. Obviously, when people ask questions, that means they've tried it and maybe they got hung up on it. Hopefully, you've been keeping up with it because you've got to in order to be ready. Right? Should I walk around and do a homework check? Yeah. I don't mind doing that, but I would like to give everyone the opportunity of getting 100 on a quiz for having their homework, right? Okay. How many of you would want me to do that? Let's see. We're only about half. Okay. Here's the thing. We walk a fine line here. Okay. This is. I got to say this in a nice way. I don't want you to take it wrong, but this is college, right? This isn't. I'm not here to babysit anybody. I give you an assignment. I tell you to do it. That's what you're supposed to do. You don't do it. You don't do it. But that only hurts you. So, all right, let's go. What do we do here? This is a bunch of letters and it's all messed up. We look first at the root. It's a higher root, cube root. Inside we have a negative, right? Can we do negatives? Cube roots of negatives? Yes, odd, negative, good. We can do that. And what we know is that what will come out is a negative from it, right? Okay, let's now look at the other things. Everything else is a letter. This C here, right, is like C to the first power, right? The H is to the 27th, the K is to the 24th. So this is where we started saying how many times does this go into this, right? So what am I saying? For the C, what am I saying to myself? How many times does 3 go into 1? It doesn't. So that means we cannot break that c down, which means the c is going to stay there, isn't it? So it's going to stay. How about for the h? I'll take care of the c in a second. How about for the h to the 27? We say how many times does 3 go into 27? 9 times evenly, right? No, nothing left over. So that means I can represent that on the outside as an h to what? 9th power. Okay. How about, no. It's how many times does 3 go into 27? So 9 times. Now, the next one is k to the 24th. So how many times does 3 go into 24? 8 times evenly, right? Without anything left over. So k to the 8th. And so what's the only thing left inside my root? What's still in here? I have negative c, right? Watch the way I write this. Negative 1c. Now, the reason why I put negative 1 here is because I want to ask you if you can figure out what the cube root of negative 1 is. Close? I'm going to do this on the side here. What's the cube root of negative 1? It's negative 1, isn't it? What times itself 3 times gives you negative 1? Negative 1 times negative 1 times negative 1. Do you agree? Negative 1 times negative 1 times negative 1 gives you negative 1. So the answer is negative 1, which means that I can, maybe I should go one more step to help just in case. K to the 8th. What I'm really doing is breaking this cube root into 2 cube roots. One of them has a negative 1 in it. The other one has the c in it. The cube root of negative 1 becomes negative 1, right? So I don't have the cube root anymore. I will put that negative 1 out in front of everything. H to the 9th, k to the 8th. And what's still underneath the cube root is a c. I couldn't do anything to that. And that's our answer. Still underneath the root? See, I had this one too. Isn't that the answer? 8.5. Yeah, that negative has to come out like a negative 1. Yes. You mean, can you write the whole answer with that whole root in front? Like this, and then your h to the 9th back here? K to the 8th, and then maybe, where would you want your negative? You could put it out front. That wouldn't be wrong. The only danger in that is that sometimes when people write it, they'll get real lazy with the root symbol, so I can't tell like if the h is underneath the root or if it's separated. So that's why we normally put everything that's not under the root in front, so you don't accidentally get it underneath your root symbol. But that's not wrong. And to really be clear, you could put like a dot between these to stress it's that root times the h to the 9th times the k to the 8th. Okay? All right. Mm-hmm. Yeah. And that's where she stopped? Okay, well, maybe they just oversight. Yeah. I mean, that sounds like they got you there, but didn't take care of the cube root of negative c. 23. So number 23, we have the 5th root 128. Uh-oh, that doesn't look good. A to the 10th, B to the 12th. Now, when you look at this, you're doing a fifth root, right? Fifth root. Which means we can handle a negative number underneath or positive. It doesn't matter. The only time we're ever really worried is if it's an even out there. We just can't have a negative. So here we're okay, right? And the A to the 10th should be something we can handle, right? 5 goes into 10 how many times? Twice. Let me go ahead and do that now. So I have what on the outside then? A squared. How about the B to the 12th? What's that going to give us here? How many times does 5 go into 12? B squared. Do we have anything left underneath the fifth root? We have 2 B's, right? But we also have that 128 we haven't handled, have we? We haven't messed with that? Keep in mind that fifth root, don't forget to write it, okay? It's a fifth root, it's not a square root. I know I can't break down the B squared anymore, but what about the 128? So I'm going to try and figure out if 128 breaks down to be 2 things, one of them being a perfect, not square, not a perfect cube, not perfect fourth, a perfect fifth power. The hell? So what are the fifth powers? 1 to the 5th is 1. 2 to the 5th is, what's 2 to the 5th? 2 times 2 times 2 times 2 is what? 5 times? 2 times 2 times 2 times 2 times 2. 5 times. Not 5 times 2, that's 10, but 2. It should be 32. Try it real quick. 2 times 2 times 2. This is where you break out your calculator real quick and you do it. The first 2 together, that's 4, right? 4 times 4 is 16 times 2. So 32, yes. Yes, you can have your, yeah. If you don't bring your calculator to test, you're going to be probably regretting it. Well, hold on. That's 2 to the 5th. That's 32. We need to try and break down 128. Can we get 128 even? What about 3 to the 5th? Let's just check it. What's 3 to the 5th? What's 3 times 3 times 3 times 3 times 3? That's 9. That's 9. 9 and 9 together. 81. 81 times 3. That's bigger than 128. That's not going to work. So I'm hoping that 32 goes into 128. How many times does 32 go into 128? 4 times? Does everyone agree with that? 32 times 4 is 128. And we're happy about that, right? Yes? Because what that allows me to do, and I'll come back over here to my work, a squared, b squared, fifth root, I'm going to break the 128 down to be 32 times 4, and I'll leave the b squared right next to it. That's fine. And I'm showing as much work as possible here. A squared, b squared, fifth root of 32 times fifth root of 4b squared. I'm sorry, I can't scroll up anymore. Is that too low or are we okay? All right. Did y'all see what I did there? Yep. That fifth root, so I broke up the 32 and the 4b squared. I know I can't break down the 4b squared anymore, right? 4 is not a perfect fifth power. B squared, 5 doesn't go into 2. But that 32 we know is 2 times 2 times 2, 5 times, right? So the fifth root of 32 is 2. So this guy right here turns into a 2, right? I'm going to put it right back over here. So my answer is equal to that 2, I'm going to slide it out in front of the a squared, b squared. And what am I still left with here? Fifth root of 4b squared. And that's it. My plan for the test is just to go through your homework and pick out problems and just kind of change them a little. That's all I'm going to do. It's not going to be anything fancy. All right, anything else on that homework? We need to move on a little bit here. Well, a lot of bit, I should say. Just trying to determine how much of this I really think you should know. How about this? So we're continuing now from last class. How about adding and subtracting higher roots? We're in 8.5. All we've done so far is just talked about nth roots, like higher roots. But now I'd like to add and subtract them and see what happens. Or if we can. So I'm going to put up here recall. Whenever I put recall up here, it means that you should know this from either earlier this semester or from a previous class. This is from earlier this semester. What do we get if we take square root of 3 plus 2 square root of 3 minus 5 square root of 3? What is that? Square root of 3? 0? Negative what? Negative 3 square root 3? Negative 2 square root. Boy, we have a lot of different answers here. Negative square root of 3? Well, we're trying to add and subtract, right? Roots. You can only add and subtract roots if what? Yeah, if what's underneath them is the same, right? If the roots are the same and what's underneath them are the same. Are those all the same roots? Yes? So what you look at then are the numbers in front. There's a 1 in front of that first one, right? There's a 2 in front of the second one. And there is a negative 5 in front of the third one, right? So what you're doing is you're taking a positive 1, you're adding 2, and you're subtracting 5. So 1 plus 2 is 3. Take away 5 is negative 2. So you have negative 2 square roots of 3. That's the way we did that before. Also, remember this as another example. What if we did square root of 3 plus square root of 27? Can you add those together? Not right now, right? Because they're not the same things under the roots. Agreed? But the square root of 27 can break down to be 3 square root of 3. Why? 27 is 9 times 3. And so I can break down the square root of 27 to be square root of 9 and square root of 3. And then now can I add them together? Yes, and this would become what? 4 root 3. These two examples are things that we've already done. Okay, so I'm not going to get into a whole lot more detail on this. All I want you to be able to do is now do the same thing with higher roots. So here's your first example with higher roots. All right, let's add these together. Add or subtract, whatever it shows. Cube root of 5 minus 3 cube root of 5 plus square root of 5. Can you put these roots together? Two of them you can. The third one on the end you can't combine. So here's why. First, we have addition and subtraction, right? Between there's 3 terms here. The last term right here, this last one, is a square root. I didn't accidentally leave the 3 off. I intentionally left the 3 off the root because that's a square root. Those first 2 are cube roots. You can only combine them together if they're the same roots. And what's underneath them is the same. So do we have, both of those are cube roots, right? And both of them have a 5. So what we do is we look at the numbers in front. 1 and -3. What's 1 minus 3? -2. So we get -2 cube roots of 5 and then plus square root of 5. And that would be it. That square root of 5 on the outside is just to help you remember that you can only combine them if they have the same. Now, it used to be they just have the same thing underneath, right? Because back when I showed you that, all we knew were square roots. Now that we have higher roots, not only do we have to have the same thing underneath, we have to have the same root to be able to combine them. Yep. Okay. So you can only add or subtract roots if same nth root and same radicand. Now, the thing is, you're asking for kind of an explanation, a general, how does this work? I have to use terminology that we use in math. So this right here, the nth root, is just whatever the number is here. And the radicand is everything that's underneath the root. So if you look at 2 roots, they both have the same number, okay, same nth root, and they have the same radicand, then you can add them or subtract them. All right, that's all I want you to be able to do on that, though, okay? Just be able to add them. Now we're ready to talk about a brand new concept. Still tied into this, but it's new. It's probably going to be new for a lot of you. Ready? Rational exponents. Have we talked about what rational means? What you should think about when we see fraction? Good. Fraction, ratio, right? Rational. So what I'm about to talk about are fractions and what? Exponents. And what are exponents? That's your powers. So what we're going to be looking at are when we have fractions as powers. Not fractions raised to powers, but when the powers themselves are fractions. I know. So here's what we're going to do. I'm going to start with the general definition. And we're going to come back to this. This is what we'll be able to refer to throughout the rest of today. Okay, right now, if I wrote this, I would hope that everyone would understand that means you're trying to find a number that when you multiply it how many times? Itself, n times, you get back x, right? That's what that means. Now, this right here, this x, I'm going to put a power on it. I'm going to call it m. This is equal to x raised to the exponent n divided by m. This is the big, I guess, formula if you want. This is our notation, right? On the left side, this would be called radical form, and this is rational exponents. So all I'm doing is all we're doing today is this. Everything we've done with radicals, with roots, all we're doing is having a new way of writing it, a new notation. It's kind of like, do you remember in the very beginning of math, they taught you division using that symbol right there? Right? If I wrote 4 divided by 2, that's like when you first learned math, that's the way they wrote division. And then at some point they said, okay, let's write it that way instead. Right? Okay. It's just another way of writing the same thing. That's all this is. Another way of writing the same thing. So let's not get too freaked out about it. But what we need to do is be able to use it. So let's do some examples first of converting. Convert the square root of 5 to rational exponents. I'm going to say to rational exponent form. Right now, what we have is a radical, right? It's a square root, but that's what we've got there, right? Yes? Okay, so watch what I do. I'm going to take the square root of 5, and I'm going to point some things out to you. Or maybe you can help me. What is the root? What root is this? Square. So what's the number that's out there that we don't write? 2, right? So when it's square root, it's a 2. So I'm going to put the 2 out there. The 5 is like our x. What power is that 5 being raised to right now? First power. Any number just sitting there by itself is to the first power, right? So here's our 1. Now go up and look at that formula up there, okay? The x is our 5, right? What's n for us here? 2. And what's m for us here? 1. Right? N is 2, m is 1, and x is 5. So let's rewrite this then. This should be x, which for us is what? 5 raised to the 1 over 2. X raised to the 1/2. Yes, absolutely. In fact, if you didn't have it, I would wonder. I would scratch my head and say, why wouldn't you put that on your formula sheet? Okay? So it turns out that if you take anything, watch. If you take anything, let's convert again. Square root of anything. What's it equal to? X to the 1/2. Right? X to the 1/2. So if I take this, here's our square root, here's our x. There's a 2 out here and a 1 out here, so this is the same as x to the 1/2. That's it. So when I say, it's kind of like I was saying, the old division symbol, right? The old division symbol is like what you use in grade school, and then you get to the newer symbol. Y'all remember when you used this little, it looked like an X? Remember when y'all used X for multiplication? Right? What's 41 times 23? That was your multiplication symbol, right? We stopped using that. Why? because it looks like x, right? It looks like x. And we needed to introduce x later as a variable and blah, blah, blah. So it just made sense to get rid of it. It was too basic for us. Well, same thing here. The radical notation at some point becomes troublesome. So we move to rational exponent form instead. Okay?
So that whole answer x to the half is a rational
That is an expression written with rational exponents. Let's do something else. How about writing this one? Convert negative sixth root of 1/9 to rational exponents. So I'm trying to confuse you by throwing more junk in there, like that negative in front, and I'm put a fraction inside just to kind of mess you up. But at the end of it all, if we just focus our attention on just what the radical is, there's our radical, right? What's the x for us? 1/9. What's the n? 6. And what's the m? 1 again, isn't it? Do you agree? Do y'all see that? So our answer should be the negative that was sitting out in front of the whole blue box, but then our x, which is 1/9 raised to what power? 1/6. That's it. Questions?
you have to write it in parentheses like that, or
Yes.
you
Yes. Because if you, well,
what if you I mean
that parentheses is just to separate that negative out front.
oh because it is in front of
The thing is this. Had I put the, like, let's say inside the radical at the very beginning, let's say I had put a negative in here, then that negative would have to be in there inside parentheses. You would have to have it in parentheses there. So it's just a good idea to put whatever x is in parentheses to separate it. Okay, let's try going the other way. Okay, let's take something that's written with a rational exponent, try and convert it to radical. Oh. So convert the other way. Example, convert 4 to the 3 halves to radical form and then simplify. Four to the 3 halves. I have a radical, right? 4 is our x. What is the root? What's on the outside? The 2. And so just remember that anytime you have a rational exponent, the denominator, right, the bottom number, is what's on the outside of the root. So this will become a 2 out here. That comes from here. And then what goes on the power for the 4? 3. Now that's correct, but I wanted you to simplify. So what is 4 cubed? What's 4 times 4 times 4? 64. And what's the square root of 64? It's 8.
Okay, so let me make sure you have the 64
From doing 4 cubed.
from
4 cubed, 4 times 4 times 4. For as long as I can remember, I've always wanted to do this at like my daughter's birthday party one of these years, you know? Like wouldn't it be cool to go to like kid's birthday party and then you have like the cake sitting there and then, everyone's joining around to blow out the candles. And then I do those little big wax numbers, like 4, and then I put something like the 4 here and then like maybe up on sticks I'd put like a 3 and then like a 2. Wouldn't that be cool? And everyone would be like, "What? How? Wait. She's 8. Come on." Right? Because that's what it means, right? That's 8. Yeah, you could. But I'm not that sadistic. I wouldn't mess with people like that. But that what I'm trying to get you to see here is that 4 to the 3 halves is just the number 8. And you may wonder, well, why would you ever do that? Yeah, you're right. But I'm trying to get you to see how this works. Okay, how these numbers, what that 3 turns into, right? The 3 turns into a power, the 2 turns into a root, and then you can simplify. Shall we do another? How about this one? Convert this one to a radical. See if you can do that one. If you do finish that one, do this one afterward. Tell me if there's a difference. How about the first one? Anyone want to volunteer the first? The first one, top one there? What goes inside? What's our x? Negative 64. What's the root? 4. That is correct. Is it possible for us to figure out what the 4th root of negative 64 is? No. This is a non-real number. A non-real number. And then, how about the other one? How is the other one different? Negative is on the outside of the root because I did not have the 64 in parentheses. And that's what I wanted you to see. With the 64 in parentheses raised to the 1/4, that negative 64 in parentheses becomes the x. Here, the 1/4 is only acting on the 64. The negative in front is like a negative 1 by itself. So that's why I put the negative in front. Now my 64 to the 1/4. 64 to the 1/4, which turns into 4th root of 64. Can you find the 4th root of 64? Yes, it's a positive number. You can take the 4th root. The question is, can you break 64 down? Or is 64 something times itself 4 times? Four times 4 times 4, 3 times. That would be 4 to the 3rd, but we need it to be to the fourth. What's 2 to the fourth? 32? No, that was 2 to the fifth. 2 to the fourth is 16. Does 16 go into 64? 4 times? So you could break this down to be the fourth root of 16 times the fourth root of 4. The fourth root of 16 we just said is what? 2? So negative 2 fourth root of 4. Very different problems. I mean, they look very close to the same thing, but just that parentheses changes what you can do. If you have a parenthesis, then that means that power, the 1/4, acts on everything in the parenthesis, which means everything in the parenthesis goes underneath the radical. Okay, I want you to look at this one, and we're going to talk about a property here. How about telling me what this is? Same thing, convert this to radical notation and then solve. So what would 9 to the 5 halves be? 9 to the 5 halves. What root's on the outside? 2 is the square root. I don't have to write it, but I will. And then inside is what? 9 to the 5th power. Ooh. 9 to the 5th power is 9 times 9 times 9, 5 times, isn't it? It's a pretty big number. You probably need a calculator for that. And then you're going to try and take the square root of that answer. So here's the property I want to show you. Right now, the way I have it written, I'm doing the power, 5th power on 9, before I'm doing the square root, right? That's what I'm doing. But you can actually take the square root of 9 first, and then do your 5th power. And I'll write it down more formally in the next line as a note for you with a general formula. But does that make it a little easier? If we do the square root of 9 first, then 5th power. What's square root of 9? 3. And then, whoa. And then what's 3 to the 5th power? Well, that still might require a calculator, but the number's going to be much smaller. 3 times 3 times 3 times 3 times 3. What's 3 times 3 here? 9. What's 3 times 3 here? 9 times 3. So it's 81 times 3, right? 243? 243. So here's the note that's going to allow you to do this, all right? We said earlier that if you have the nth root of x to the m, that I could rewrite that as x to the m over n, right? That's what we did. But I want you to write this next. Instead of that, write this. And then put your x to the m over n. And I'll put a little note under here. Power first, then root, This one, root first, then power. Do y'all see the difference in those first two lines? And you're allowed to do either one, okay? That's what it's saying. They're equal, which means that whenever you're looking at a radical, if you want to do the square root, or sorry, if you want to do the root of the number first, do that first. That's fine, and then bring the power in. That would be the middle one. Or you can do the power on the x first and then take the root. It's your choice. Now, I think that should take care of most of what I'm going to ask you to do for homework on numbers. But let's see how rational exponents work with variables. Okay. I think I'll start a new page. Rational exponents with variables. So before I start this, let's recall some of the exponent properties. These are things that we should know about powers, basically. If I have x to the n times x to the m, anyone remember what that's equal to? Is it n times m or n plus m? It's n plus m. So if you have different powers on the same base and you're multiplying, then you just add the exponents together. If you do x to the n over x to the m, then that's x to the n minus m. You subtract the powers. And then there's this one. If you have x to the n times raised to the m, this is where you multiply the n times m. Those properties look familiar? There's more. How about x to the negative m equals 1 over x to the n? That meant that if you have a negative exponent, you can drop it down, right? Do you remember that? Switch. If you have an negative exponent and your factor or whatever's on top, you can drop it down. If it's on the bottom and negative, you can bring it up. But that's the property for it. We also have this property. If you have a fraction to a positive power, you can apply the power to both the top and bottom like this. What if you have a fraction to a fraction to a negative power? Anyone remember what you can do here? You bring it down, but then it goes positive, but it winds up really just flipping your fraction over. This is a nice property to remember. A fraction to a negative number really just turns into flipping the fraction over and changing it to positive. These are good to know going into what I'm about to show you. Because now what we're going to do is we're going to imagine that all these n's and m's now, which you're so used to those numbers being like 2, 3, 5, 7, right? Whatever, just numbers like integers, nice. Now they can be fractions. All those numbers can now be fractions. So let's mess with those. So let's do this example. Let's multiply this. What's x to the 1/2 times x to the 3/5? So the property I'm using for this one is going to be this one, x to the n times x to the m, right? X to a power times x to a different power. The formula says that this should be equal to x to what? N plus m, so 1/2 plus 3/5, right? And now the question is, can you add two fractions together? Common denominators. You have to get common denominators. So I'm going to do this on the side. I need to do 1/2 plus 3/5. How did you learn to add two fractions like that together? Common denominator? Most of you get what would a common denominator here be? 10. So you have to multiply the first fraction by what? To get 10 on the bottom. 5 on top and bottom. And then on the other one, you multiply 2 top and bottom. So this right here becomes what? Multiply straight across. 5 over 10. And then this one over here becomes what? Multiply straight across. 6 over 10. Now that you have the same denominators, 5 plus 6 is 11 over 10. Right? So 1/2 plus 3/5 is 11/10. So our answer is x to the 11/10. Now I'm not asking you to switch this over to radical. That's our answer. But just FYI, this would be the 10th root of x to the 11th, wouldn't it? And does 10 go into 11? One time, right? With how many left over? 1. So the 10th root of x to the 11th is actually x times the 10th root of x. But that's just extending on what we've already kind of talked about. What would this be? I'm going to give you some problems to work on here. I think this might be my last example. What's 32x to the 1/5 time raised to the 2/5? And we have a lot of things going on here. I think, yes. You mean multiply the 1/5 and the 2/5? Yes. But what do we do with the 32? So here's a property that I'm going to use. I actually didn't write this property down, so it might be good to write it. The property is that when you have two things that multiply together, x times y, and you're raising the whole thing to a power, that power goes to both the x and the y. So in my problem, over here, I want you to look at the 32 as kind of like the x, and the x to the 1/5 as the y. So it's kind of like, here's your x, here's your y. So I have to raise both the 32 to the 2/5, and I have to raise the x to the 1/5 to the 2/5. Do y'all see that? Let me write it down, maybe it'll become clear. I need to take the 32 and raise it to the 2/5. Then I need to take the x to the 1/5 and raise it to the 2/5. Can you see that? Can you see that that is this property over here? Let's look at the 32 to the 2/5. Let's quickly convert that to radical notation and see if we can figure out what it is. Maybe I should do it on the side. I'll do it on the side. 32 to the 2/5 is the same as what root? 5th root of 32 to the 2nd. I don't want to square 32, do you? So I'm going to square on the outside. In other words, I'm going to take the 5th root first and then square. What is the 5th root of 32? We did that, didn't we? 2. What's 2 squared? 4. So we have the 5th root. We have 32 to the 2/5 is equal to the 5th root of 32, but that answer squared. The 5th root of 32 is 2. 2 squared is 4. So I could put that on a birthday cake too. 32 to the 2/5. I like that better, right? So this is a 4 right here. Now, the other one, this one here, I have to use the property that says if you have something to a power, then to a power again, what do you do with those powers? 1/5 and 2/5. That would be if they're side. That would be if I had them side by side. But if it's like if I had this x to the 1/5 times x to the 2/5, then I would add them. But because it's like this, I multiply them. 1/5 times 2/5. And that's a good thing because when you do multiplication of fractions, it's just straight across. 2 over multiplication. 2 over 25. 2 over 25. So x to the 2 over 25. Okay, let's see, it's 12:02. Let me just give you maybe 3 or 4 problems for you to try. See if any of this has gone in today. And I'll put at the end of it your homework assignment. Let's see if you can figure out, let's see, we did that already. How about find, first one, what is the 4th root of 2 minus 8 times the 4th root of 32 plus 5 times the 4th root of 2. Convert to rational exponents. And I'll give you a couple here. Square root of 17. I'll make this larger if you can't read this. That should be good. I don't think I'll have enough time to finish all that. There you go.